In this video, we are going to look at force friction. There are 4 different parts to this video that we will look at that pertain to force friction. The first part will be the variables involved with force friction. The second part will be the graphical relationship of force friction. The third part will be deriving the equation from the graph for force friction. And then the fourth part will be completing a problem for force friction. So to look at an enlarged view of force friction for surfaces in contact, you can see that the surfaces have a roughness to them. So force friction always opposes the sliding motion. So in order for an object to move, it must rise to where the peaks can skip along the bottom surface. A force is required to set the object in motion, and that's what we would call that force applied. And the force friction, we would call it, would be that force static friction. And then some of the peaks eventually will break off and you can maintain a force to keep the motion. That would be the force friction kinetic once it's in motion that we'd be relating to. But much of the force is actually due to the attractive forces between the molecules that make up the two substances. So that would have to do with the composition of what the two surfaces are made out of. That determines a large part of force friction. So these force friction variables, one is the type of surfaces. When we look at the type of surfaces, this is also related to the coefficient of friction. We are going to use this symbol right here to represent the coefficient of friction. That symbol is a Greek letter, mu. And so that means it depends on what is the composition of the surfaces. The second one has to deal with the force normal. This is due to the force pressing the two surfaces together. We noticed in the lab, as we kept putting more mass on the blocks, the force's friction increased. And that's what happens when force normal increases, pressing those surfaces together, there ends up being more friction between the two objects. The next one is the surface area. Many times, most people think their surface area has an effect. Surface area does not have an effect on force friction. So in other words, this does not have a relationship. So it is not included in our equation. So this force versus time graph is an example of, we'll say, a block that is being pushed on a level surface. So we're going to say we have this force applied, and then we're going to have a force friction. And then, of course, we know we have force gravity and force normal. And those two forces are congruent, so we're not going to have to really deal with those. But in this situation, what this would mean is this static friction, this would mean that right in this area, your force is increasing as you are pushing on the block, but there is no movement yet on the block. So this would be no movement. This, at the very peak here, this is where the point at which the block begins to move. And then this segment right here, it is varying a little bit, and that's because of that roughness of the surface. That would be the block is sliding. And there's a little variation in the force there, and that's because we're trying to keep it at a constant speed, so there is a little variation with that. Now, this first segment right here, we would call this force friction static, when it isn't moving yet. Once it does move, we call this force friction kinetic. So that breaks down the two types of frictions that we have for an object. Now in this graph, we graphed force normal, as we were changing the force normal, the mass on the block, according to the force friction. Now, I have 2 lines on here. This one is the relationship, since it is a steeper slope, this would be for force friction static. Okay, so that's when just graphing that. And then this one, with less slope, this would be force friction kinetic. Okay, Now, they're both a linear relationship, so we know that that basic equation is y equals mx plus b. So we can do the equation for each one of them. The only difference would be the slope value. And so we'll talk about that. So we could substitute in if we're talking about force friction static or force friction kinetic. So if I was looking at, let's say, this example right here. So if I looked at what's on the y-axis, it looks like it's my force friction. So I'm going to go force friction, and I'm going to go static equals m, we know, is the slope. Now, this slope value is really, if we look at it, it is really one force divided by, so this would be force friction divided by force normal, because it's the rise over the run. So if you notice that, it would be newtons over newtons. They would cancel out. It has no units. Now, the slope, we give a special letter to it. This is that letter mu. It looks like that, okay? And that letter, we give it the special name. It is called the coefficient of friction. So in other words, this tells us about the roughness of the surfaces. That larger that value is, the rougher the surfaces are. X, in this case, what's on the x-axis? That's the force normal. Force normal. And then if we looked at this, yes, these should run through 0, 0, so this really ends up being 0, so we don't even have to deal with that in our equation. So this is our equation right here. Now, the thing is, when you use this mu for force friction static, you got to make sure that you use the coefficient for static friction. I can rewrite this equation. It would be the same exact equation for the force friction kinetic. The only difference would be is that I would use the mu, or the slope, for kinetic, and it's still the force normal. So that's the equation that we are going to use to figure out our either force friction, or we could figure out the coefficient of friction, possibly force normal. So if we look at a coefficient of friction table, this is just a guide. You'd have to do the actual experiment to figure out what they are. But if we have two different surfaces on here, you can see, like if I had aluminum and steel, they give you the coefficient of static friction is 0.61. Of kinetic friction, it is 0.47. So in each case, you can see static friction is greater than kinetic friction. So just looking at some examples of those for comparison. So now, looking at a problem in your book. In your book, this is on worksheet 5, it's problem number 4. The first thing that we are doing is we are having, I believe it is a book that is being pressed against the wall. As this book is being pressed against the wall, they want you to figure out what the coefficient of friction is. So I believe on part A, you need to draw a force diagram. So we'll start with that, just like we have with our force problems. We have force, friction, upward, and force, gravity, down. Now, this is at rest. So we know this should be congruent to this. And then you're pushing it, so we can say force applied. And then this would be our force normal. And so we know the push, that this is 15 newtons. So then our force normal, we know, is a negative 15 newtons. Okay, so to put those on here. Now, part B asks you to figure out what is the force minimum so that this doesn't slide, so we know it's got to be at rest. So if we're looking at these forces, so for this to slide, we're going to, if that would be in the vertical direction, we're going to look at summing those two forces. So for part B, we would say force, gravity, plus force, friction, and this would be static because it's at rest, equals 0 because it's balanced. Okay. So then we know to figure out force gravity, it's m times g. So the mass of this book, I believe, is 0.5 kilograms times gravity, which is that negative 9.81 newtons per kilogram, plus that force, friction, static equals 0. So when we calculate this out, we get a negative 4.905 newtons plus force, friction, static equals 0. So this means our force, friction, static has to equal 4.905 newtons. Okay, so yes, those are equal. So we know this is a negative 4.905. So now we know that this is a positive 4.905. Okay, so that figures out our force minimum needed to keep that book on the wall without sliding. Now, the next thing that they wanted you to figure out was, in that B part problem, was the coefficient of friction. So we're talking static, so our equation is force, friction, static equals mu static times force normal. Okay, so we know what our force friction static is. We just figured that out. That was 4.905 newtons equals this mu times the force normal. The force normal we know is right here because those forces, these are congruent because this is at rest. So if I did this, force normal, we know that's a negative 15. So if we did our math, now we always do absolute value on mu, so this ends up being 0.33, and there are no units on mu. It's just, this is what it is. And usually they use the simple mu equals 0.33. And that's just telling you what is the roughness of the surface.